Today we're covering something called matrix algebra, and it's basically applying the basic algebraic operations to matrices. So to start off, we want to recall that an m by n matrix, an m by n matrix that we're going to call A, is a rectangular array of numbers, and again, this is important, we have m rows, so the number of rows goes first, and n columns. And then we also say that because of that, matrix A has a dimension of m by n. So that's what we call a dimension. And again, it's rows, then columns. The individual numbers that make up the matrix are called elements or entries. I'm going to call them entries. And if we denoted one, we could say in matrix A, one entry would be I, J, just so that you know that the rows go first. So the I would be the row number, and J would be the column number. And we always start from the top and go down and left to right. Column number. All right. So for example, here's matrix A, and we have a bunch of numbers in there. And the dimension of A is the number of rows, which is 3, by the number of columns, which is 4. So this is a 3 by 4. And if we looked at sample entries, A1, 2, that means first row, second column. First row, second column, that entry is a 7. A3, 2 would be third row, second column, that entry is a -1. And A3, 4 would be third row, fourth column, that's going to be an 8. We can also define equality of matrices. Basically, the matrices, if I call one A and another one B, they are considered equal if and only if, that's what that IFF stands for, if and only if they have the same dimension and corresponding entries are equal. So I'm going to show you that down here. These two matrices are considered equal because they have the same dimension. The first one is a 2 by 3, and the second one is also a 2 by 3. And then if you look at their values, the square root of 4 is equal to 2, 2 squared is 4, e to the 0 is 1. They all have equal values when you simplify them. The next matrix, the numbers are the same, but they are unequal because the first one is a 3 by 2, and the second one is a 2 by 3. They have to have the same dimension to be equal, the same number of rows and the same number of columns. So that's what equality of matrices is all about. The next thing we're going to talk about is the sum, difference, and scalar product of matrices. So if two matrices have the same dimension, otherwise this isn't going to work. If they have the same dimension, then they can be added or subtracted. Their entries can be added together or subtracted. So here's a more formal definition. We define two matrices. A is this and B is this. The IJ means that they have the same dimension and they're m by n. And then C is going to be any real number for these three definitions. So the first definition is this. The sum of those two matrices is, if they're both m by n, your answer is going to be at m by n. It's the m by n matrix obtained by adding corresponding entries in A and B. So here's what that looks like. I'm going to say matrix A is 1, 2, 3, 4, and matrix B is going to be 5, 6, 7, 8. Doesn't really matter. Then if I want to add A to B, they are the same. They have the same dimension. That's just going to be 1 plus 5, 2 plus 6, 3 plus 7, and 4 plus 8. So 1 plus 5 is 6, and then 6 and 2 is 8, and then 10 and 12. You are adding corresponding entries. So the difference between the matrices, that's going to be the m by n, same size, matrix obtained by subtracting corresponding entries. So it's the same process, we're just subtracting instead of adding. Again, they have to be the same size, so let's say that matrix A is going to be a 2 by 3, 1, 0, 3, 5, 2, 1, and matrix B has to be a 2 by 3 if we're going to subtract 8, negative 2, 0, negative 1, 5, 4. Then A minus B is going to be the difference. 1 minus 8, that's negative 7. 0 minus a negative 2 is 2. 3 minus 0 is 3. 5 minus a negative 1 is 6. 2 minus 5 is negative 3. 1 minus 4 is negative 3. And that's your answer. You're just subtracting corresponding entries. And then finally we have something called the scalar product. And we need to call it the scalar product because pretty soon we're going to learn something called the matrix multiplication, which is different. The scalar product is going to be the m by n matrix obtained by multiplying every entry by some number. We call that a scalar. This is like a dilation. When you think of dilating a point, you multiply every the abscissa and the ordinate by that number. It's the same thing. So if I have matrix A, and he is 1, negative 2, 3, and 5, I can represent 2A. It's basically dilating every value. It's 2, negative 4, 6, and 10, and that 4 looks terrible. Okay, so that's what a scalar product is. So I'm going to have you guys do the next operations, and then we will check them in class. We are going to dimension them together, though. So the first one, we're going to dimension these matrices. A is a 3 by 2. B is going to be another 3 by 2. C is a 2 by 3. And D is a 2 by 3. So you guys are going to go and do parts A, B, C, and D, and then we will check them in class. Alright, so now we're going to talk about matrix multiplication. And it's different than the scalar product. And the process is unique, and you have to kind of learn the process and understand how it works. And sometimes it takes a little bit, but that's okay. We can spend class time right after this lesson and then probably another day practicing matrix multiplication. So you will get it down. So we can multiply matrices A and B, denoted AB, only when the number of columns in A is equal to the number of rows in B. So the order matters. I'm talking about A first and then B. If we can multiply in that order only when the number of columns in A is equal to the number of rows in B. So here's what this looks like. What you would do is line up, put a matrix A first and then B, and then dimension both of them. Let's say A is an m by n, and B is an n by k. When you line them up, if the middle numbers match, that means we can do this matrix multiplication. So the middle numbers must match. Otherwise, it's not going to work. So again, the middle number represents, this guy is the number of columns in A, this is the number of rows in B. So they have to match. And then the answer you get, the result is actually an m by k when you're done. So that's kind of cool. So we always want to line up and dimension our matrices for matrix multiplication, because first we can check to see if we can do it, and then we can figure out how big the matrix is going to be when we're done. So the result is an m by k. Alright, well, if we're going to multiply matrices, we first have to define something called an inner product. Because this is basically the process that we do to multiply. So I have a row in A. Let's call it A, B, C. Let's say that's one row in A, and I have a column in B, D, E, F. Then the inner product is what you get when you multiply A times D plus B times E plus C times F. We are not distributing, okay? We are not distributing A into all of these. We are multiplying corresponding parts, row to column, row to column, row to column. So the inner product would be this, AD plus BE plus CF. So what do you get when you add all these up? Am I going to get a polynomial? Am I going to get a whole bunch of numbers? This represents the sum, and the sum is going to end up as one number, one value. So every time you take the inner product, your answer is going to be a single number. So we're going to find the inner product, all the inner products we need to when we multiply matrices. So here's a numerical example. I've got 2, negative 1, 0, 4, and I'm going to multiply that by 5, 4, negative 3, 1/2. So the 2 goes with the 5, the negative 1 with the 4, the 0 with the negative 3, and the 4 with the 1/2. I always go left to right and up, down. So 2 times 5 plus negative 1 times 4 plus 0 times negative 3 plus 4 times 1/2. 10 minus 4 plus 0 plus 2. So I think that's 8. Again, we get a single number when we're done. Alright, so before we do this, and before I show you with an example, we're going to write down some steps. To multiply matrices, the first thing you do is you make sure you line up your matrices, put them in correct order, and write the dimensions. So if I want to multiply A and B, the order matters. If I'm going to multiply A times B, you got to put them in that order. You dimension, if this is an M by N and this is an N by K, that means we can do this. The center values have to match, and the result is going to be an M by K. So that's what we do first. We make sure we can do this, and we kind of figure out the result. And what I do is I kind of lay out the result. So I'll show you that, I guess, with this. If I have matrix A, and he's going to be a 2 by 2, so he's going to have A1, 1, A1, 2, A2, 1, and A2, 2. So he's a 2 by 2. And I have matrix B. Matrix B is going to be a 2 by 3. B1, 1, B1, 2, B1, 3, B2, 1, B2, 2, B2, 3. So B is a 2 by 3. That means I can take their product because the inner values match, and the result is going to be matrix C. The result's going to be a 2 by 3. C11, C12, C13, C21, C22, C23. I always lay that out so I know how many values I'm calculating. Again, it's a 2 by 3 because the outside number is the number of rows, and this outside number is the number of columns. So I'm going to make 6 calculations. That's 6 inner products I should produce when I do this problem. And then just as a reminder, the inner dimensions must match when you line them up. So what I do next, the first thing I want to calculate C11, and that means I want to multiply row 1 by column 1. So here's how I find C11. I'm going to find the inner product of the first row in A by the first column in B. And I'm not going to do all these here, but I will show you C11. So C11 is going to be A11 times B11 plus A12 times B21. So C11 is A11 B11 plus A12 B21. So you're always going across in the first one and down in the second one. Okay, and then what you do, once you get done with that one, you multiply the first row in A with the second column in B. So here we find the inner product of A11 B12 plus A12 B22. So again, we're always going row, column, 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 and then when I'm done with the first row, third column to make C13, I do the whole process over again with the second row, first column, second row, second column, second row, third column for C11, C21, C22, C23. So I repeat everything with the second row. It's really confusing at first, and I know I get that every year with students. I'm going to walk through one numerical example, and then we're going to practice this quite a bit in class. All right, here's our example. We have A, we're going to just dimension it right off. A is a 2 by 2, B is a 2 by 3. We want to calculate A, B, and BA if possible. Well, first off, if I look at BA, that means I have 2 by 3 and 2 by 2. That's not going to work. The inner dimensions don't match. So BA is not going to work. But AB should work because the inner dimensions are 2 and 2. And then I'm going to get a 2 by 3 as an answer. So here's my 2 by 3. C11, C12, C13, C21, C22, C23. So I have to make 6 calculations when I do this. C11. That's going to be the first row, first column. 1 times -1 plus 3 times 0. C11 is going to be -1. C12 is going to be first row, second column. First row, second column. So C12 is going to be 1 times 5 plus 3 times 4. And that ends up being 5 and 12, 17. All right, the next one is C13. That's going to be first row, third column. So he's going to be 1 times 2 plus 3 times 7. That's 21, 22, 23. That should be 23. So we've got our first row done. -1, 17, 23. Now we do 3 more. C21. He's going to be -1 times -1 and 0 times 0. First row, or second row, first column. So he is -1 times -1 and 0 times 0. So that's going to be +1. I'm going to fill them in right there. C22, if you can look at it, you could see second row, second column. So that's going to be -1 times 5 plus 4 times 0. So that's going to be -5. And then finally, C23 is second row, third column. That's going to be -1 times 2 plus 0 times 7. He ends up being -2. So you might want to watch this again. It takes a while to get it down. We're going to practice it in class, but after a couple days, you should be able to do this just fine.